Hey everyone, in this video we'll talk about rational expressions. Suppose that we have polynomials p and q of x, where q of x is not equal to the constant function 0. Then the quantity p of x divided by q of x is what is known as a rational expression. Basically, I earn the word rational expression when I'm a polynomial divided by another polynomial. And again, we're simply just saying that q of x is not equal to the number 0 for every value x. This just ensures a non-zero denominator. But a couple of examples. The polynomial x squared plus 3 by definition is a rational expression because I can express it as x squared plus 3 divided by 1, and by definition, constants are polynomials. So every polynomial is a rational expression, but not every rational expression is a polynomial. The next example has x squared minus x minus 6 divided by 3 minus x. The top and bottom are both polynomials, so this is a rational expression. Now let's look at some non-examples. The numerator of this first example has a square root of x and x raised to a 7 divided by 2, making it not a polynomial. The second one has sine of x in the denominator, also not a polynomial. So these are two fraction expressions, but they are not rational expressions. Again, the numerator and denominator have to both be polynomials to earn the word rational. The main topic of this section is learning about how to simplify rational expressions. So suppose that we started with x squared minus x minus 6 divided by 3 minus x. I noticed that the numerator factors as x minus 3 times x plus 2. I also know that in the denominator I can factor out a negative 1, revealing the exact same factors upstairs and downstairs. Now our intuition tells me that these would cancel each other out, and they do, we just have to be careful. Our cancellation law goes as follows. If p of x, q of x, and r of x are all polynomials, where q of x and r of x are not equal to the 0 function, then p times r over q times r is equal to p divided by q. In other words, if r of x is a like factor of the numerator and denominator, it does cancel out. So we can apply this to the example above. We'll let those x minus 3 terms cancel each other out. This leaves me with negative x plus 2, giving me negative x minus 2 as an answer. But we have to pay attention to one thing, the concept of restricted values. Imagine if I had plugged in the value of 3 for x at the very beginning example. Then I would have a divisor of 0, which is not okay. I would actually have an undefined term. So restricted values essentially protect us from that. A restricted value is a value of x that causes the denominator at any stage in the problem to become a 0. So let's look at our problem. The only denominator here was 3 minus x. We're going to set that equal to 0 and solve. This tells me that when x is equal to 3, I have a denominator of 0, which is not allowed. So we'll tag 3 as a restricted value and state that x cannot equal to 3. So the main strategy here is the following. When I look at a rational expression, I want to factor the numerator and denominator as much as possible and see what cancels out. But at the end of the problem, I keep track of every single term that is or was in the denominator, and I use those terms to look for restricted values. Even if that term cancels, as our 3 minus x did, I still have to record the restricted value that came from that canceling term. Really quick to talk about cancellations, let's talk about some common mistakes that can be made. So we'll call this slide when not to cancel. Suppose I have x squared plus 4 divided by x squared. Even though I see x squared both upstairs and downstairs, that's not enough to say it's a canceling term, because x squared, while it's a factor of the denominator, is not a common factor of the numerator. So saying that the above expression is equal to 4 is a false statement. Similarly, I can't take x squared plus 4 divided by x and do this kind of cancellation. If I were to say everything on this second line is equal, it is also a false statement. I only get to cancel terms if they are common factors of the entire numerator and the entire denominator. Now let's simplify the following rational expression. Start with x cubed minus 8 divided by x squared minus 2. The numerator factors with our difference of cubes formula, and the denominator has a GCF of x. Just a quick comment, this video does assume the understanding of factoring principles, so if you need to review those, go back to the section 1.3 videos, watch them again, or look at the section 1.3 or 1.4 notes. But back to the example at hand. After we've factored the numerator and denominator, we can see a common factor of x minus 2. So we're going to cross those out and end with x squared plus 2x plus 4 divided by x. And we know we're done because x is not a common factor of the numerator, so this rational expression is fully simplified. But next we have to look at our restricted values. The denominator factors of x and x minus 2 are what we need to pay attention to. We're going to set each one of them equal to 0 and solve for x. What we find is that x is not allowed to take on the value of 0 or the value of 2, because plugging either of these into the beginning expression would give us a 0 denominator. So we'll say that x not equal to 0 and not equal to 2 are the restricted values of this rational expression. For our next example, look at x squared plus 5x minus 6 divided by x squared plus 4x minus 5. Factoring the numerator and denominator with the AC method gives the following. And we already see a common factor of x minus 1, so we can cancel those out and get a finalized, simplified expression, x plus 6 divided by x plus 5. Even though they canceled each other out, we still have to check every denominator factor. So we're going to set x plus 5 equal to 0 and x minus 1 equal to 0. Solving for x in each case says that x cannot be equal to negative 5, nor can it be equal to positive 1, because both of these values, when you plug them into the original problem, give us a 0 denominator. If you recall finding the domain of rational functions, the process is very similar. You factor the denominator, set it equal to 0, solve for x, and see which values you're not allowed to be. For our next example, take a look at the expression x minus 3 over x plus 5 plus x squared plus 3x plus 2 divided by x minus 3. Just as with numeric fractions, I can add these together if I have a common denominator, so I'm going to have to find one. But first, I'm going to factor that second expression to look for cancellations. It's always good to have this in factored form as you're working with these. I don't have any canceling terms, so I'm going to multiply that first fraction by x minus 3 over x minus 3, and then I'm going to multiply that second term by x plus 5 over x plus 5. This is like multiplying by 1, which we did in the rationalizing the denominator section. The whole point is to get us common denominators. So let's take our time and write this out. I take the first fraction and multiply it by x minus 3 over x minus 3 because that's the other denominator. Then I take the second fraction, multiply it by x plus 5 over x plus 5 because that's the other denominator. Even though terms are going to stack up in the numerator, we know that each denominator is going to be x plus 5 times x minus 3, and then we can finally add these fractions together. And as I said before, it's good to leave everything in factored form. So I get x minus 3 squared over x plus 5 minus x minus 3 plus x plus 2 times x plus 1 times x plus 5 over x minus 3 times x plus 5. Now with common denominators, I can add the numerators like so. At this stage, we'll have to multiply all the terms in the numerator. This comes from using the distributive property as we did in section 1.3, but the final result that we get is x cubed plus 9x squared plus 11x plus 19 divided by x minus 3 times x plus 5. I'll go ahead and give you some assurance and say that you are not expected to factor polynomials that are cubic like this. This is a harder factoring problem, and unless something specifically nice happens, you're not expected to try to factor a numerator like this. So for our intents and purposes, the answer is done. This irrational expression is simplified, and now we can move on to finding the restricted values. So every factor in the denominator is going to be x minus 3 or x plus 5. Setting these factors equal to 0 and solving will yield restricted values of 3 and negative 5. Let's get some more practice with this. Now we're going to combine the expression x plus 2 over x minus 3 minus x minus 3 over x plus 5 minus 1 divided by x squared plus 2x minus 15. This is a big problem, so let's keep our eye on the strategy here. First, we want to factor everything as much as we can. The first two fractions can't really be factored anymore, but that denominator in the third fraction can be factored with the AC method. That fraction becomes 1 over x minus 3 times x plus 5. So the idea is that all of our denominators have either an x minus 3 or an x plus 5 in it. So let's go ahead and try to find that common denominator. That first fraction we'll see gets multiplied by x plus 5 over x plus 5, and the second gets multiplied by x minus 3 over x minus 3. But these first two fractions are going to have a common denominator of x plus 5 times x minus 3, which is already matching that third fraction, so it does not need an extra multiplier. Just to recap, that third fraction multiplied as x minus 3 times x plus 5, so that denominator did not need any kind of upgrading, whereas the first two denominators did need to be upgraded. But now everything has the same denominator, so we can go ahead and combine these fractions. Once we add and subtract all the numerators together, we obtain the following quantity. And then what we're going to do next is expand or FOIL all these out and then simplify. So multiplying out that numerator is going to give the following quantity. And after some distribution and combining of like terms, it simplifies quite nicely because what I end up with is simply a numerator of 13x and a denominator of x minus 3 times x plus 5. Now for the restricted values. Again, I have denominator factors of x minus 3 and x plus 5, and those will yield restricted values of positive 3 and negative 5. So just some quick commentary. That was a long problem and it took a lot of steps. This is the kind of thing that takes practice, but when you are combining rational expressions in this course or in Calculus 1, you can have a lot of things to do at once. So the purpose of this problem is teaching us some good bookkeeping habits and some organization. Remember, the key goal is to factor as much as possible and find common denominators. Next, we're going to multiply and divide rational expressions, which might sound worse, but it's actually easier than adding or subtracting them because I don't care about common denominators anymore. But let's review a couple of rules with fraction multiplication and division. A over b times c over d means that I just multiply the numerator and denominator. But a over b divided by c over d means that I just take that second fraction, turn it upside down, or take its reciprocal and turn it into a multiplication problem. So a over b divided by c over d equals a over b times d over c, which gives me ad over bc. None of these rules care about common denominators, so we will find that multiplication and division problems with rational expressions are easier than addition or subtraction problems. Let's look at an example. Z squared plus 2z plus 1 divided by 2z squared plus 3z plus 1 times 2z squared minus 5z minus 3 divided by z plus 1. Yeah, that's a tongue twister. But even though this is a multiplication problem, let's first factor each term as much as possible. Everything on that left fraction factors with the AC method, and everything on the right fraction also factors with the AC method. So what we get after factoring is a numerator of z plus 1 times z plus 1 over 2z plus 1 times z plus 1 multiplied by 2z plus 1 z minus 3 over z plus 1. Let's take the extra step of combining these fractions into 1 using our multiplication rule. And at this point, it's just going to be cancellation galore because I see a lot of things that are canceling. I got 2 copies of z plus 1 upstairs and downstairs, and a copy of 2z plus 1 upstairs and downstairs. So what I get left with is z minus 3 over 1, which is just z minus 3. And last but not least, we have some restricted values to look for. Now I have to look at every factor that is or was in the denominator. Even though no denominator terms other than 1 survived, we still have to check them. Setting the values 2z plus 1 and z plus 1 equal to 0 and solving for z gives me restricted values of negative 1/2 and negative 1. Next, we'll consider a division problem. So we're going to divide the following 2 given rational expressions. Our division rule says to take the fraction that's on the right and reciprocate it, or flip it upside down. Then we can rewrite our given expression as the following. It's going to be y squared minus 11 plus 24 over y plus 6 times y plus 6 divided by y squared plus 5y minus 24. Now the expressions in each one of these fractions is factorable with the AC method. So let's go ahead and perform those actions. The numerator on the left becomes y minus 8 times y minus 3, and the denominator on the left becomes y plus 8 times y minus 3. Now be careful, because that y minus 8 and that y plus 8, even though they look similar, they're not the same terms. They do not cancel. The signs are not exactly the same, so they will survive the problem. But after we combine these fractions into 1, we'll see that the y minus 3's and the y plus 6's do cancel. So once I perform those cancellations, I get a final answer of y minus 8 divided by y plus 8. Now we got to check for all of our restricted values, and this is everything that is or was in the denominator. The only factor that was not ever in the denominator was y minus 8. That stayed in the numerator the entirety of the problem, but the other 3 factors, y plus 6, y plus 8, and y minus 3, were in the denominator at some point. So we're going to get restricted values of negative 8, negative 6, and positive 3. In our last example, we're going to look at a complex rational expression. Basically, it's going to be one like this where I have a fraction within a fraction. And yeah, it does look awful. But we always got to remember that this is pre-calculus, the goal of which is to prepare us for Calculus 1, and one of the biggest hurdles in Calc 1 is the algebra. You do encounter expressions like this, and we need to get some practice with them. The first thing that we're going to do is we're going to factor out that denominator of h in the following way. I can write this as 1 over h times the entire numerator quantity. In other words, 1 over h times the quantity 1 over x plus h minus 1 over x. And what I'm doing is exercising the following rule. A divided by b is the same thing as 1 over b times a. Here, imagine capital B is that h by itself, capital A is that entire first numerator. Next, I'm going to distribute that 1 over h to each of the fractions within. This gives me 1 over h times x plus h minus 1 over h times x. It's still quite a bit of terms, but this is a little bit easier to look at than what we started with. This is a difference problem, so we still need to find a common denominator. We're going to multiply that first fraction by hx divided by hx, and then that second fraction gets multiplied by h times x plus h over h times x plus h. Again, we're just using the other denominator to construct that multiplication by 1. Okay, so let's go ahead and multiply each individual fraction, which gets the following. We see that the denominators are the same, so we can go ahead and combine our fractions into 1 by subtracting the numerators. Moving on to the next slide, we'll start noticing that there are some canceling terms. That numerator upstairs has a common factor of h, so I can factor that out, and that cancels with one of the h's that's already present in the denominator. In other words, h divided by h squared just leaves me with an h in the bottom. So after that h cancels and I distribute that negative in the numerator, I have x minus h over hx times x plus h. Next, those x's in the numerator cancel out additively, leaving me with one copy of h upstairs. And then I see even another cancellation of h's happen. And this gives me a final answer of negative 1 over x times x plus h, and we're finally done. As I was saying before, Calculus 1 does have a lot of algebra that is assumed when you come in, and you're going to be working with something known as the difference quotient, and that's going to produce complex situations like we just saw. We've all heard that saying in the South that says it's not the heat that gets you, it's the humidity. Well, when it comes to Calculus 1, it's not the Calc 1 that gets you, it's the algebra. This section and your instructor are very aware that rational expressions and fractions in general are just tedious because they take a lot of step. So take this section seriously, please watch the video again, please look at the notes, and please reach out if you need help, want to see more examples, or have questions or anything.